Hello, this is Christine O'Connor, and this presentation is on polarimetry and circular dichroism. So polarimetry, the term polarimetry may be referred to as the study of the rotation of polarized light by transparent optically active substances. This is a type of qualitative and quantitative analytical technique as both identification and estimation of the compound can be achieved. So you can either find out how much of a substance is there, or you can also find out if the substance has converted from one form to another. So just before we start talking about polarimetry, we need to look at the important basic concepts. So we need to look at the definition of asymmetry as opposed to symmetry. What does optical activity mean, and what is polarized light? So in principle, the polarimeter measures the rotation of polarized light as it passes through an optically active substance, and the tendency of the molecule to rotate the plane polarized light towards clockwise or anti-clockwise direction, whose extent of the rotation can be measured. So basically it's your sample can deflect the light source either to the left or to the right. So these compounds are called optically active compounds, and optical activity is a unique character for a molecule. So in this diagram we look at unpolarized light. It goes through a polarizer and forms plane polarized light. So polarization of light waves can occur using what's called polarizers. So these are just diagrams to explain what a polarizer does and what plane polarized light looks like. The optical activity of a substance, then, there are two types. So first of all, there's dextrorotary or right-handed. So the substance which rotates plane of polarization of light towards the right or in clockwise direction are called dextrorotary or right-handed. Levorotary or left-handed, the substance which rotates plane or polarized light left or in anti-clockwise direction are called levorotary or left-handed. So just in the example here we have lactic acid, and this is the dextrorotary lactic acid, and this is the levorotary lactic acid. So they have the same elements and atoms around the carbon, it's just they're in a different order. The instrumentation then, so a polarimeter consists of a polarized light source, a sodium vapor lamp, a polarizer which is usually quartz prism material, and an analyzer which is a nickel prism, aligned to intercept the linearly polarized ray as it emerges from the sample solution, which is a graduated circle to measure the rotation angle and through the sample tube. So you have your light source, your polarizer, and this is shining through your sample compartment. Okay, so it's very important that this sample compartment is filled with your sample made up in its liquid, usually in water, and that there's no air bubbles in this. And it's also important that the glass windows at each end of that sample compartment are clean. So you can clean them with lens tissue if there's any fingerprints or dirt on them. And then that goes to the detector. What are the applications of polarimetry? So identification, determination of optically active compounds. Optical activity is the only one parameter for distinguishing between delta and lambda isomeric forms. Where would we see these applications in the real world? So first of all, if you end up in the chemical industry, many chemicals exhibit a specific rotation as a unique property, like that of refractive index. So this can be used to distinguish between chemicals. In the food, beverage and pharmaceutical industries, polarimetry is used for the concentration and purity measurements are done to those samples that have specific rotations that can be calculated for purity with a polarimeter. And examples of those are steroids, diuretics, antibiotics, vitamins, analgesics, amino acids, essential oils, polymers, starches, and sugars. In the sugar industry alone, polarimeters are used in the sugar industry for determining the quality of both juice from sugar cane and the refined sucrose. Often the sugar refineries use a modified polarimeter with a flow cell called a saccharimeter. Polarimetry of thin films and surfaces is commonly known as ellipsometry. So that's all we're going to say about polarimetry. Now we're looking at circular dichroism. So circular dichroism, or CD, spectroscopy is a form of light absorption spectroscopy that measures the difference in absorbance of right and left circularly polarized light by a substance. Circular dichroism phenomena is that results when asymmetrical molecules interact with plane polarized light. So this is an example of a symmetrical achiral compound. So all of the atoms attached to the central atom are the same, whereas an asymmetrical chiral compound, so this is your chiral atom, and you have 4 different atoms or molecules attached to that chiral atom or chiral center. So this is asymmetry. So we have an example here of alanine in the levorotary and dextrorotary position. And these can also be described as S enantiomers and or enantiomers. Okay, so like before, we talked about light and light sources, and we've already talked about wavelength, speed of light, the frequency and the amplitude. But really, when we're looking at light here, we're looking at polarized light. So again, it's the use of a polarizer that splits the light source into polarized light. And the different types of polarization then. So you've plane polarized light, which we've already referred to, and we said that this is used in the polarimeter. And then in the circular dichroism, we use circular polarization. So the light ray passes through a filter which has 2 vibration directions. So it causes the light to be in a circular form rather than in a single form. The function then of nitrogen purging in circular dichroism, which is just bubbling with nitrogen, is to remove oxygen from the lamp housing, monochromator and the sample chamber. So you really want to eliminate oxygen from the instrument using nitrogen. And the reason for this is the presence of oxygen is detrimental for 2 reasons. When deep UV light strikes oxygen, ozone is produced. So ozone causes degradation of optics, and it can cause respiratory problems for the person carrying out the analysis. The second reason for removing oxygen is that oxygen absorbs deep UV light, so thus reducing the light available for the measurement. When preparing samples then for measurement, you may come across different additives, buffers and stabilizing compounds. So any compound which absorbs in the region of interest should be avoided. So again, just be careful that you're looking at buffers that are not coming into the same wavelength range as your analysis. When you're dealing with protein solutions, the protein should contain only those chemicals necessary to maintain protein stability and at the lowest concentrations possible. Any additional protein or peptide will contribute to the CD signal, so they'll add on to the circular dichroism result. And the data collection then, so initial experiments are useful to establish the best conditions for the real experiment. Cells of 0.5 millimeter path length offer a good starting point. So typical initial conditions for circular dichroism are the protein concentrations are quite dilute. It's 0.5 of a milligram per mil. The cell path length is 0.5 millimeters. Stabilizers are kept to a minimum, and the buffer concentration is 5 millimolar, which is 5 by 10 to the minus 3 molar, or as low as possible, while maintaining protein stability. So just to bear in mind the wavelength that different solvents absorb at when you're using, or buffers also, when you're using circular dichroism. So again, you don't have to remember these, but it's just to show you if you were using circular dichroism that this is where these would absorb. And for data analysis then in circular dichroism, the molar ellipticity is related to the difference in extinction coefficient. So here molar ellipticity has the standard units of degrees per centimeter cubed per decameter per mole. So, or sorry, per decimole. So the molar ellipticity has the units degrees deciliters per mole per decimeter. This is just an example of a circular dichroism spectra of calf thymus DNA titrated with a compound. So just to show you, on the x-axis it's wavelength in nanometers, and on the y-axis it's this delta E, which is the change in ellipticity. So applications of circular dichroism spectroscopy. One of them is the estimation of protein and nucleic acid conformation. Another is the determination of conformational changes due to the interactions of asymmetric molecules, such as protein-protein interactions, protein-DNA interactions, protein-ligand interactions, and DNA-ligand interactions. So ligand is just a small organic molecule. Determination of the thermodynamics of folding and unfolding of proteins and nucleic acids. Other applications are determination of binding constants, using direct titration, serial dilutions of compounds, changes in stability to thermal or chemical denaturation of DNA. So for example, if we're testing compounds to see if they are anti-cancer compounds and if they have DNA binding affinities, we would use circular dichroism to do some of those measurements. Another application is kinetics of folding and unfolding of macromolecules. So circular dichroism of proteins. So it has been shown that the circular dichroism spectra between 260 and approximately 180 nanometers can be analyzed for the different secondary structural types, such as alpha helix, parallel and antiparallel beta sheets, turns, and others. So a number of excellent review articles are available describing the technique and its applications, by Woody in 1985 and Johnson in 1990. Modern secondary structure determination by circular dichroism are reported to achieve accuracies of 0.97 for helices, 0.75 for beta sheet, 0.5 for turns, and 0.89 for other structure types. So we can find out a lot about proteins using circular dichroism. So the signal then for proteins will mainly be concerned about the absorption in the UV region of the spectrum from the peptide bonds and the amino acid side chains in proteins. So protein chromophores can be divided into three classes: the peptide bond, the amino acid side chains, and any prosthetic groups. So the lowest energy transition in the peptide chromophore is an N:¿pi transition observed at 210 to 220 nanometers with a very weak intensity. So this diagram here gives you a nice example of what this would look like. So the first one there, the black line, is your alpha helix, and this is the spectrum you get in the circular dichroism. The blue dotted line is your beta sheet, and the pink dotted line is your random coil. So you can see that quite easily you'll be able to interpret three different forms of your protein in terms of using circular dichroism, because they give very different results. The other thing that's quite useful is for chromophore analysis. So you'll see that below 250 nanometers, the chromophore you're identifying as the amide, which is a secondary structure. Between 250 to 300, you're looking at aromatic groups, which is a tertiary structure or folding. And above 300 nanometers, you're looking at extrinsic groups, which again could be due to ligand binding. So again, you don't have to learn off any of these details. It's just summarizing where you would see negative bands and positive bands for each of these types of protein structures. And the total signal for a protein depends on its secondary structures. So again, here's an example of 4 different types of protein structures and how they would differ in their spectra. To get more information on circular dichroism, you can look up this website, and this will give you other examples, or you can compare your samples against a library of spectra there. You can also use circular dichroism to monitor tertiary structures of proteins. And you can use it for peptide binding to nucleic acids. So you can monitor the difference here, for example, at different pHs, a pH 5 and a pH 7, and how the peptide is binding to the nucleic acid. And this is just an example then of protein-protein interactions. So again, you can see that there's a dramatic change in the spectra before and after. So in summary, the circular dichroism spectroscopy is used to gain information about the secondary structure and folded state of proteins and polypeptides in solution. The benefits of circular dichroism are that it uses very little sample, like 200 microliters. It's non-destructive, so you can get your sample back. And relative changes due to influence of the environment on the sample, such as pH or denaturance, temperature, can be monitored quite accurately. The drawbacks then are the interference with solvent absorption in the UV region. Only very dilute non-absorbing buffers allow measurements below 200 nanometers. The absolute measurements subject to a number of experimental errors, and the average accuracy of fits about plus or minus 10%. And the circular dichroism spectropolarimeter is relatively expensive. Now we do have one of those instruments in our research facility in this institute.